Welcome back to another video. Today we are here talking about the exam style questions for week 1. So I'm just going to step you through how to answer these problems. So let's start out with the first one here. So the question is requiring us, I'll just get up my pen there. So the question is requiring us first up to find the maximal domain of a particular function. So when you're asked to find the maximal domain of a function, the very first thing you want to ask yourself is when will this function be undefined? What you're looking for is square roots and numbers down the bottom of fractions, so numbers that are being divided. So if there's a square root of an x, if we're dividing by an x, they're the first things you want to look at. Also logarithms and all that kind of thing. We'll get to that later. So if we look at this thing underneath the square root sign, what are the restrictions on that square root? Well, the thing underneath the square root has to be greater than or equal to 0. So x plus 1 needs to be greater than or equal to 0, right? Which tells us that x needs to be greater than or equal to -1. So what I'm going to do is I'm going to start working it out down here. So we have here the function f(x) is equal to 1 plus the square root of x plus 1. And we know that x plus 1 needs to be greater than or equal to 0, so we get that x needs to be greater than or equal to -1. So therefore, what is the maximal domain of this function? Well, first up, what's domain? Domain relates to the x values or the inputs of the function, and we know that the input into this function can be basically anything, excluding numbers that are greater than or equal to -1. So we could write it like this, for example. We could say it is including -1 and then anything larger than that. We could also write it like x is going to be, well, x is allowed to be, put x in the middle here, x can be greater than or equal to, how do we write this? Yeah, so x can be greater than or equal to -1 or strictly less than infinity. We could also write it like that. So both of those would be valid ways of writing this information that we've been given. So in other words, yeah, we just need to state what possible x values could the function take. All right, so that question, pretty straightforward. Part 2, we need to find the inverse of this function. So we're asked to find f to the power of -1. F to the power of -1 being the inverse function, which is to say we're going to swap the x and the y values. So that is exactly how we answer this question. We start by swapping the x and y values around. So here's our original equation, y equals 1 plus square root of x plus 1. So to find f -1, so that there was f of x, say f of x. To find f of -1, we're going to just swap these two values. So I'm going to take what was the x value, and I'm going to write it out the front here. And I'm going to take what was the y value, and I'm going to put it underneath the square root sign. So I'm just swapping the two values. All right. Now I just need to rearrange this equation to make the y the subject. So that will involve minusing 1 from both sides, firstly. And then squaring both sides over here. And then minusing 1 from both sides and just putting the y neatly on the other side of the equation. So that's going to give us y is equal to x minus 1 squared minus 1. And that y that we just found there, that's the inverse y, so the inverse output. So that's why we name it f to the power of -1. Now that is not the answer. The answer requires us to make some comment about the domain of this function. So an important thing for you to remember is that only 1-to-1 functions have inverses. And conversely, the inverse is always going to be 1-to-1. We can't have a parabola as the output like that, because a parabola is a many-to-one type function. It is a function, but the inverse will not be a function. You can see that that will fail the vertical line test if we swap the x and the y axes like that, which is the same as saying if we tilt the thing on its sides. So what we need to look at here is the domain and range of our f function. So we know that the domain of f of x was equal to x is greater than or equal to -1. We got that from part A. Now, an important thing for you to realize is that the domain of the function is going to be the same as the range of its inverse. So therefore, the range of this function's inverse will be y is greater than or equal to -1. It's the exact same as the domain, because remember, the x and the y values have just swapped. So what was the x on our function is now the y of the inverse function. And by the same token, if we can find what the range of the original function was, that will give us the domain of the inverse function, which is what we want in order to write this thing in function notation. So let's just see if we can figure out the range of f of x. So the range of f of x, well, let's have a think about this. The y value here is going to be equal to 1 plus something, and this thing over here can be no smaller than 0. So it's not possible to have the square root of a number, so the square root of 7, the square root of 3, whatever it might be. It's not possible to have a square root of a number that's going to come out as a negative, and the thing underneath here can be no less than 0, so it's not possible for this to be any less than 1 plus 0, which is just 1. So we can see here that the lower bound of this, y, must be strictly greater than or equal to 1. Again, if we put in our limit of the domain, if x is equal to -1, we're going to get -1 plus 1, which is 0, square root of 0 being 0, 1 plus 0 is equal to 1, and that's the minimum possible value. So if that's the range of our original function, that will in fact be the domain of the inverse function. Get rid of that. The domain of the inverse function. So therefore the domain of the inverse function will be x is greater than or equal to 1. And if we put all of this together, we can now write the inverse function in function notation. First thing you do is you give it a name, so I'm calling it f inverse. Second thing we do is we state what its domain is. So its domain is x is greater than or equal to 1, which we can write as 1 to infinity. Be sure to get this in the correct order, so the smaller number comes first, then the larger bound there. We go arrow r, so that's the domain, this is the codomain. We're putting in a number between 1 and infinity, and we're going to get out a real number. And then we simply state the rule for this function, which is x minus 1 squared minus 1. All right, so that there is the inverse, and its domain and range I've already stated over here. So the domain is x is greater than or equal to 1. Range is y is greater than or equal to -1. All right. Next step, we need to sketch these two graphs on the same axis. Okay, so starting this one out, I'll put down my axes over here. So let's just put down some axes. I'll give myself a little bit more space down the bottom so that my face doesn't cut out the answer. So let me just go and click here. I'll go insert pages, blank page. All right, there we go. Okay, so let's scroll back down here. Let's go back to where we were. There we are. So we're going to try and sketch our axes. So I'll just chuck in an XY axis right over here. Not super accurate, but that's all right. It's just a rough sketch for the purpose of this video. So we know that, so this is going to be our Y, this is going to be our X. We can see here that we're dealing with the numbers -1 and 1, so they need to be somewhere on our axes. So let's just go up in intervals of 1, and if we need to change our intervals to fit in more important values, we can do that later. So again, this is just pretty rough. Let's do that again. All right. Don't know why that happens. Let's go back down here. So put in our points. All right. So let's start by drawing our original function. So I'll put that one in green. So this is going to be f of x, which was equal to this function here. So the original function was 1 plus root 1 plus x. All right, so what does that look like? Well, this is a square root function that has been shifted to the left 1, and it's been shifted up 1. So it's going to look like something like this. It's going to start at this point over here, which is negative 1, 1. It's going to go up. When will it pass through 0? Let's have a think about that. So to find y-intercepts, we're going to let x equals 0. So when will x equal 0 in this equation? Well, x will equal 0 when y is equal to 1 plus the square root of 1, square root of 1 being 1, so that's going to be equal to 2. So we're going to get this point here lying on our graph, which is 0, 2, and then that kind of gives us a feel for how this graph might look. So it's going to come up like that, and it's going to go off in that direction over there. All right, moving on, let's look at f of negative 1. So f of negative 1, or f inverse, we found the equation to be x minus 1 squared minus 1. So this here is a parabola that has been shifted to the right 1 and down 1. So it's going to start here at the points 1, negative 1. And similarly, when will y equal 0? Because we want to find what the x-intercept is. So we want to find, let's do it in the same format as above. So we want to find the x-intercept, because we want to know when it passes through here. So we let y equal 0. So therefore, putting in y equals 0, we get this. We can bring the 1 over to the other side. And we can square both sides. So we get 1 squared is 1. And then we can add 1 to both sides. So that's going to get us x is equal to 2. So that's going to be right here. We get 2, 0, and we can see that the parabola will look something like that. All right. Finally, what do we do for part D? So part D asks us, what is the coordinates of the point of intersection between the two graphs? So where do the two graphs overlap each other? The coordinates of this point over here. Whenever you're asked to find the coordinates of the point of intersection, essentially all you have to do is to make the two graphs, make the two equations equal each other and solve. So for part D, we're going to make the two equations equal to each other. So in other words, make f of x equal to f of negative x. So f of x is going to be 1 plus the square root of 1 plus x. And that needs to be equal to this equation that we had for f of negative x, which is x minus 1 squared minus 1. And we're simply just going to solve that. So I won't do that by hand. You'll be given a calculator for one that's this challenging, because there's quite a few solutions to it. But if you know how to use your CAS calculator correctly, all we have to do is go action, and then, it is under advanced, solve, and then you can just type it in there. I think there's another button for it, so it's been a while since I've done this. Action, advanced, solve. If we type in action, advanced, solve, we can then type in this expression. We have 1 plus the square root of 1 plus x is equal to x minus 1 squared minus 1. And then we go comma x to say we want to solve x. And then we'll put that into standard form. Okay, so it's telling us that there are a couple of possible solutions to this. So it's giving us x could be equal to 3, and x could be equal to negative square root of 5 over 2 plus a half. Now, which of these two solutions should we accept, and which one should we reject? So let's have a look at what we're actually dealing with here. So when would that second solution occur? We can see that 1 will clearly occur up here. The other solution would occur if we were to continue this red graph. If this wasn't restricted in its domain, go up here, then we're going to get possibly another solution here. But remember, we've cut the graph down the middle. We're only including the top half of that parabola. So we can ignore this intersection point over here and just focus on that one. So in other words, we're just trying to figure out which of these two intersections is larger than the other one, and that's likely going to be that point there. So we're using the context. Or we can restrict the domain using the calculator to just include numbers that are greater than 1, because we know that's our domain here. So which of these is greater than 1? Well, let's put it into standard form. You can see that number there is clearly less than 1, so we must include the x is equal to 0. So x is equal to 3. So that there is going to be the one that we will include, and that's the x value of this point of intersection. And then finally, to find the y value, just substitute that into either one of the equation. So for example, y at this point, if we just use the original equation, is going to be equal to 1 plus the square root of 1 plus 3, substituting x equals 3 in. So that gives us 1 plus the square root of 4, which is 2. So that's 1 plus 2, which is 3. And then we can see that the point of intersection right here must be 3, 3 as the coordinates. All right, so moving on, looking at this question here. So this question asks us, a piece of fencing that is 960 meters long will be used to enclose 3 sides of a rectangular field. The fourth side has a straight channel. We're going to let L be the length of the field and let A be the area of the field. And the question is asking us to express A as a function of L. So whenever you have a question like this, it's like a modeling question, it might be useful to just list out the information that you know and see if you can do anything with that. So let's just sort of go line by line into this question. So the first sentence says, a piece of fencing is 960 meters long. It's used to enclose 3 sides of the rectangular field. What does this look like if we were to put it into equation form? So we've got the number 960. What is 960? That's the perimeter. So it's the distance from here to here to here to here, because we're only enclosing 3 sides of the field with the channel left open. Let's say we call this distance here C. You can see that L plus C plus L should add up to make the total perimeter of this shape. And we know that the total perimeter, that's the fence. So the fence is going to be equal to, so 960 will be equal to 2 times L plus C. Right, so hopefully you can see where that equation came from. It's using the fact that the total distance around the outside is 960. All right, so the second sentence says, let L be the length of the field shown, and we're going to let A be the area of the field. Now, what do we know about area? Well, area is given by length times width, and in this case, length is called L, width we've just called C. A little bit confusing, but you can see here that the area is going to be equal to length times C. Question 1 requires us to present A as a function of L. So that's like just a function of L. We don't want to have any C's in that equation. So how can we write an equation that looks like this? Right now we have that A is equal to L times C. How do we eliminate C? Well, we have this other equation up here. So maybe we can use this equation. We can somehow substitute it into this equation and we'll get rid of C. So here's how that might look. We want to eliminate the variable C, so let's rearrange this equation to make C the subject. If we minus 2L from both sides, we get C is equal to 960 minus 2L, and then we can go ahead and just substitute that straight in here instead of C. So the equation then would become L times C, which was 960 minus 2L. All right? If we expand out this bracket here, we're going to get that is equal to 960L minus 2L squared. And you might even see that there are common factors here. We can just leave them outside of the brackets, to be honest. It will make things easier for us. So we can take out the 2L as a common factor. That leaves us with 960 divided by 2, which is 480 minus L. And that's the expression. That there is A as a function of L. So question 2 asks us, what is a suitable domain of this function? So properties that we need to be aware of when we're dealing with real-world applications is there will be restrictions that will be created from the context, not just from the mathematical formula. So when we're talking about area, length, perimeter, all of these things are lengths. Lengths need to be greater than or equal to 0. So we can say this. So A, L, P, they are all greater than or equal to 0. So we need to make sure that this graph never falls below 0. So that gives us our first restriction because we're trying to find the restrictions on the domain, which is that the restrictions on L. So we know straight off the bat that L needs to be greater than or equal to 0. If we look at this equation, we have A of L is equal to 2L times 480 minus L. We know that area also needs to be greater than or equal to 0. So we can put that restriction in there. And we can see when else would this be less than 0. So obviously if L was less than 0, this will be a negative area. But also if we just look at this bit here, 480 minus L greater than or equal to 0. Both of these numbers need to be positive. Of course, if one of them is negative, then we're going to get a negative answer. It won't work. So when will this be less than 0? Well, if we add L to both sides, we're going to get 480 is greater than or equal to L, or in other words, when L is less than, L needs to be less than or equal to 480, otherwise the area is going to be less than 0. So putting all of this together, we see that L needs to be greater than or equal to 0, and it also needs to be less than or equal to 480. And that is, in fact, the domain of this function in order for it to remain positive. So that's the suitable domain. All right, and then finally, question 3. I'll do this one over here so that my face doesn't get in the way. Just bring up a graph. So we're only going to be plotting this for positive values of A and L. So there's no point in drawing the negative part of the Cartesian plane. Just keep in mind that graphs are contextual, so sometimes there's certain information that you don't need to include. So we're going to write AL up the top there, L down the bottom there, and we need to figure out what the domain of this function is. It says use a graph to determine this, so let's just do this on the CAS to start off with. Going to graphs and tables, I'll clear this from the last time I was using it. And I'm just going to type in the two equations. So I'll just write in x instead of L here. So this is my equation, 2x times 480 minus L, minus x, sorry. Don't forget the brackets. We tick this, we click this button here, and we can't see a graph. So how can we make ourselves see our graph? Well, we can go up here and we can see if we can try a few things. So first thing you might want to try is go zoom and click auto. Still doesn't really fit very well. Let's try and zoom out a little bit better. So let's go zoom out. Let's see if we can see a shape. Can't really see it still. What else can we try? We can go original. Doesn't really work too well. What else could we do? We can also select bounds on this. Have I plugged in everything correctly here? It should be correct. Auto. Well, we're trying to find what the maximum of this parabola is. So where's the peak of it? So we can actually find that using the analysis tool. We can go analysis, gsolve, fmax. That'll take us to the function's maximum. And it is telling us down the bottom here that the function's maximum will occur at 4.3 with that as our y value. So let's just plug that in. We can see here that if we consider our domain, the minimum x value or the minimum L value is 0, the maximum L value is 480, and it's telling us that the maximum y value is way up here at 4091.2, way up the top here. And it looks like it's closer down here than it is to being up there. So it's going to look something like this by the looks of it. Something along those lines. So, yeah, I think that will be correct. It's not working too well on here. I mean, Desmos does a better job of this than anything else. So let's maybe bring that up. And let's just type back in the equation. So hopefully this works a little bit better. Okay, so here's our function again. Where's that maximum occurring? It's way higher than that. So it's up here. So yeah, it should be in the middle of the domain. So that answer didn't really make any sense before, did it? So this is 280 in the middle here. So 280. Of course, this being the minimum value, this being the maximum value, the maximum should occur right in the middle of that parabola there. So that does make sense. And I suppose, well, okay, another strategy you could try in this case. Okay, so your CAS calculator is not working. What do? Don't panic. Let's say we know that the area is going to be at a minimum when L is equal to 0. So when L is equal to 0, you can see in this equation that we will get 0 times this. So the area will be 0. That's going to be an area of 0 if L equals 0, and if if L equals 480, area is also equal to 0 in this case. So we know those are our two x-intercepts. We also know that parabolas are symmetrical. So that means that there exists a line of symmetry about the center, and that the maximum of the parabola will occur on that line of symmetry. So we can draw that in like so. So the maximum will occur in that line of symmetry point. So all we have to do is find the center point, which we said is 240, because that's 280 divided by 2, and just substitute that into the equation and see what the maximum value will be. So I'll just do that on the main calculator screen. So if I substitute that into the point, we can define a function here. So we can go action, I believe it is calculation, whereas define has been quite a long time. It's important that we learn how to do these sorts of things. Define right there. So if you want to define a function, I'm going to call this function, let's call it A. I'm going to give the expression 2x times 480 minus x. That's the rule for this equation. And then if I type in A of 240, that gives us an output. There we go. That gives us an output of 115,200. So that there we can see is equal to 115,200, and that will be the maximum point. So 240, 115,200. Okay, so there's a few different strategies there. You can use Desmos. I tried the graphing calculator. Didn't work. I'm not really sure. I'll see if I can figure it out after this video. But you can see that there was another way of answering that question using the CAS, if you recall your knowledge of quadratics. So anyway, that was a bit of a confusing end to the video, but hopefully that helps you answer those questions. All right, that's all for today. I will see you guys in the next video. Have a good day.